Hey guys, Matt Dickens here, this time with a whiteboard video. Today, I'll be showing you how to add ultrasonic range finding to your next project. This method is great because it allows you to increase accuracy and range while decreasing component count and therefore cost. A quick background, ultrasonic range detection works by using a signal to resonate a transducer transmitter that changes electrical signals to ultrasonic waves. Each transducer has a particular frequency at which this works best. When the waves are transmitted, they run into objects and bounce back to a receiver transducer. The material changes the received signals from ultrasonic waves back to electrical signals. The receiver output is then compared to a fixed voltage reference, and when the output goes above the reference, the signal is recorded. A microcontroller uses the time it takes the waves to travel from transmitter to receiver to calculate the distance of the object. In the classic method, the microcontroller would send a pulse to an off-chip ultrasonic range-finding external device. The device used several components to generate the appropriate frequency and to amplify the waves returning to the receiver. Once the device had processed the sequence, it sent the signal travel time back to the microcontroller. The firmware on the microcontroller then processed the time and converted that to distance. This can be a simple but expensive solution to range finding. Note that the range and accuracy are based on fixed external components, which also increase cost. Therefore, the system can be improved by increasing the range without increasing the power usage and by decreasing the component cost. The PIC16F1769 provides an efficient solution that brings the majority of the signal processing on chip and a hardware approach that minimizes CPU processes and power consumption. The transmitter wave is created by combining peripherals to create the final signal required to resonate the ultrasonic transducer. Two timers input to the configurable logic cell, or CLC, which outputs a pulse. The PWM module is configured to create a signal at the correct frequency for the specific ultrasonic transducer. The digital signal modulator then gates the PWM signal for the length of the CLC output pulse by combining the signals together. This newly produced signal causes the transducer to output ultrasonic waves. Completing this process in the hardware cuts down external components to a minimum. The peripheral solution using the PIC16F1769 also adds two improvements over classic systems. First, a delay is created and implemented using the hardware limit timer and a CLC to minimize the effective noise due to residual vibration from the transmitter. Second, this method uses a programmable ramp generator to generate a decreasing voltage reference. This still prevents noise during the short range, but also allows distant signals to return and trigger the capture at farther ranges, even though the waves would have significantly attenuated. In the classic method, components were necessary to amplify and time the signal return to the receiver. However, the receiver hardware in the PIC16F1769 does this for you. After amplifying the signal, the system uses a capture module and a timer to capture the time it takes for the comparator to register a received signal, and gives this time to the firmware for processing. Because the received signal is processed mostly on the microcontroller, it is no longer necessary to use most of the components on the range-finding device. This saves extra component costs and, with hardware improvements, actually improves the system capabilities. The firmware is only responsible for recognizing the time value has been captured and converting that to a distance. That is the overview of the ultrasonic rangefinder application. This is Matt Dickens, and thanks for watching. For more information on how to implement this design, check out the information included below.